All right. Welcome, everyone, to Southwest Research Institute. My name is Ryan Mcbee. I realize that my email is left off of here. It is just my first name, last name at SwRI.org. And if anyone has questions at the end, I can get that to you, and these slides are going to be published later, is that correct? Yes. I'll make sure to update these slides with all of my information in case you need to contact me. But my presentation today is going to be on adapting visual simultaneous localization and mapping for space. And it's a broad set of technical topics. And for this presentation today, I think I'm going to just move through a lot of them very quickly to give you a taster of it and kind of let the questions come in about this, because it is a very wide set of skills, and I would be surprised if anyone here had like intimate knowledge of all of these different details. So I imagine there's going to be lots of questions. And so with that, a bit of an introduction about some of these things. What is SLAM, first and foremost? SLAM is simultaneous localization and mapping. And so the localization part of that is determining relative or absolute 3D location and orientation. So how much have you moved? How much have you rotated relative to the moon, another object of the such? And then the mapping portion of that is creating a map of a location that you're within, so that way if you ever come back to it, you can recognize that. So that's very useful if you are navigating in a space and you go through a couple hallways and you come back, or you want to understand where you are over time. For this research specifically, we focused more on the localization aspect of this and less so on the mapping, but mapping is on our future roadmap for what we would like to adapt for this. And so a bit of an overview of this research. I'll actually skip through. It's like, what is the task we are doing for the SLAM algorithm? So this is actually an internal research project that was focused around how do you create, we wanted to, for our space robotics efforts, how would we have a robotic arm that is connected to a satellite with propulsion grab onto an uncooperative satellite? So this research we would want to use in things like in-space assembly and manufacturing, getting uncooperative satellites that have lost, orbit or other things, and kind of just gain more control. And so the piece of research that I worked on in this grand scope of the research was, how do we build a computer vision system that can accurately measure the rotation and the translation of this uncooperative satellite, so that way a robotic arm could effectively grab onto it. And so the overview of this research that I did was, we needed to use cameras because in space, there's a lot of limitations of LiDARs are going to generate a lot of mechanical heat and draw a lot of power. And so that was already kind of off the table for an in-space application. We needed to run this in real time on space-rated hardware. And we needed to create an algorithm that was both robust and reliable to a wide range of lighting conditions, satellite conditions, and other visual systems. And so the challenges that we had to overcome, and that I'll kind of speak more to in these slides, is how do you generate images for this algorithm? We are not using a machine learning approach, so it's not like we need tens of thousands of images to train this, but a computer vision algorithm still needs to be evaluated. So how are you going to generate appropriate images for this kind of task of tracking a satellite in space? Then once we actually generated that data, how do we generate a robust algorithm that can work in various different conditions? And then the final portion of this research was, how do you design and take this algorithm and run it on space-rated hardware? So the first topic is generating space image on Earth. And so the difficulty is it's hard to collect images in space. You're not going to just take your iPhone out, step into space, and go and take images of these satellites. And so how are we going to generate these? So this is actually a data set by another research group called the Speed Plus data set. And these are examples of images that they collected with a giant sun lamp. And you see off the satellite, it's causing large amounts of glare. It's kind of saturating a lot of the features, which is a big issue in computer vision. And so whatever algorithms that we need to create need to be robust to these kind of situations. But how are we going to test our algorithm in the very unique situations that we find in space? Because in space, you're going to have you know, a very high saturated light source, the sun. You can add your own lighting source, but, you know, you can't really take away lighting unless you're in like a certain position. A lot of the satellites have very different characteristics to what you would find in Earth. So a lot of these algorithms rely on, you know, assumptions of a man-made structure, such as like distinct features, corners, and of the such. Satellites really lack that because they're, you know, just the different kinds of features that you're looking at are very different. And so we had to figure out how to characterize a lot of these things. And so what we ended up using was, you know, simulating the images. We weren't able to actually build and demonstrate real-world blacked-out environment. That's actually being currently developed, and we're about to finish that. That's actually, I believe, a tour that you can do during lunch on Wednesday to go and see our soon-to-be blackout room on campus. But we decided to do simulating of our images, and so we leveraged Unreal Engine 5. We found that it was able to model the materials and the lighting to a degree that we found sufficient for our research. It also gives us full control over the motion of the object, which is super important, and especially giving us, because it's simulated, we know the exact translation and rotation and various other parameters that, you know, we can use to evaluate our data. So at the bottom image is actually an example of us using simulation for some of our autonomous ground vehicle research. So this is actually a simulated image on the left, simulating urban and natural environment. And on the right is actually a stereo depth map, kind of showcasing the capability of what kind of labels and information can you generate from simulated data. This was supposed to be a video, but I think it didn't translate as well. It was supposed to showcase this is actually one of our attempts at, oh, it does play. Fantastic.
You can use the mouse if you want.
Yeah, I tried playing it earlier on my Google Slides, but I guess it didn't work. So this is just one example of us modeling a satellite. We're using Unreal Engine 5, so we're using a lot of their newer materials to model the metallic properties of the base of the satellite. These are stock solar panels that we were able to get from the various asset stores. And what this is showcasing is in the top left, the simulated satellite. The top right is the final algorithm that I'll talk about later, the points that it's finding. The bottom left is the stereo map, and on the right side is actually the calculation of what is the change in rotation over time. Oh, there we go. So that's us generating the images. So once we had those generated, we then had to evaluate what kind of SLAM-based algorithm do we want to start with. And particularly, you know, we focused on the localization aspect, but adding the mapping aspect is something we plan to do in the next stage, and I can talk more about that if anyone's interested later. So within SLAM algorithms, there's a lot of different subcategories that you can choose, but one of the key designations is an indirect versus a direct SLAM. And so in this case, an indirect is referencing how are you describing the image that you are comparing. And so these SLAM algorithms need to say, okay, I have image 1 and then image 2. How do I tell how it moved in that scene? And so the image at the bottom is actually showcasing for one of the pixels of that fish, how do you describe that pixel such that if I see that fish again, I can instantly know this is that same location. And so an indirect method uses various techniques, typically image gradients, around that pixel to then get a descriptor of what it is. And so this is kind of a unique fingerprint to that object. So it's actually describing the image in an indirect way. Spoiler, we use direct SLAM, which actually directly uses the pixel values instead of creating this intermediate value. And there are various different reasons why we chose that over an indirect SLAM. So this is a bit of a tech stump, but you know, we looked at indirect SLAM first. It is the most common type of SLAM algorithm that you could find. Orb SLAM is one example, but there's many others. And these work really well in terrestrial applications where you have a lot of very unique features that you can work with. But for us, that really didn't work well because A, a lot of the key points that we were finding were not unique, and B, calculating an indirect fingerprint is actually very computationally expensive, and we found that it didn't really map well to space-rated hardware. And so that really lowered our chances of actually deploying this in a meaningful way. Whereas with the direct SLAM, it uses the direct pixel value. So it actually makes the computation more clear, which I can describe later. But it also does not rely on having to use having to have very unique locations, which for the satellite image, I know it's a little zoomed out, but a lot of times for the algorithm, it was actually finding these descriptors on the actual solar panel itself. And if you look at the different ridges, it's looking for unique corners. It was matching them to various different parts. It's hard to get a unique fingerprint when you have a satellite with a lot of repeated features to it. And so we found that the direct SLAM was able to overcome that by not having to use the corners just by proxy of how the algorithm works, and B, it's able to use a lot more of them in tandem to help it. And again, I can answer any questions. These are entire papers worth of knowledge that I'm kind of skipping over right now. And so a bit more of the direct versus indirect continued. The key point matching was very difficult for indirect, and we just could never get it to work reliably. Let's see. And so the other part of this algorithm is the stereo part of it. So one of the issues with computer vision applications is what's called the scale ambiguity, which means if you have a single image, there are the famous examples of someone leaning on the Leaning Tower of Pisa, and it looks like they're as big as the tower. Well, that's the ambiguity that, looking through an image can provide for you. You really don't know what it looks like. And so a stereo camera pair is when you have two cameras, it's very similar to how our eyes work. And when you space them apart and you look at the two images, you can actually figure out how far away the object is based on how shifted those two, the same object is in the two scenes. And so we ended up going with a stereo pair option for this. And the general algorithm for the initial processing, the direct processing of the image, is we take in the left and the right image, and we calculate the stereo pair from that. We downsize both of the images for computational efficiency, and then we calculate the gradient, and then we find the unique areas that we actually want to be matching between. And so this, the finding of the edges, go back to this very long adjective dump, direct, so that's the type of SLAM algorithm, sparse, so we're not using all of the pixels in the scene, we're using just a sparse amount of edges and corners, spread across for computational efficiency, SLAM algorithm. And so this is the first stage of the algorithm, the initial image processing. So finds the unique areas, it downsizes it, does the stereo processing, and then actually calculates the gradients and edges that we need. And so now that we have the resized image, the image gradients in the depth map, we can then do all of these sparse calculations. So all of that information is able to be used to then say, all right, I have image 2. How do I, rotate and translate image 2 to fit into image 1? And that is the higher level application of this direct sparse algorithm. I glossed over a lot of things, but I'm happy to ask questions about that later. And the final part of this is how do we map this onto space-rated hardware? And for this, we did FPGA development. So kind of comparing, a CPU, a GPU, and an FPGA, the most common computing sources in space, CPUs are, lower in computational efficiency. They're very easy to use. The coding complexity is low, and the space heritage is high. And so for things that don't require high processing, CPUs are great. GPUs, they're more efficient than a CPU, less than an FPGA. They're a little bit more complex to work with. And the heritage is, starting to get there, but, it is not as ubiquitous as FPGAs and CPUs. And for us, we chose an FPGA because it has the highest amount of efficiency from what we found, especially for computer vision applications. It has the highest, space heritage. But the issue was the coding complexity was very high. And for computer vision applications, these are very complex algorithms, lots of moving pieces. And to do it by hand would be very tedious and probably more than the budget that we had to do this research. And so one of the big things that we used and leveraged in this is a tool provided by Xilinx called Vitis HLS, HLS here meaning their high-level synthesis software. And this greatly accelerated the development. And Vitis HLS, for those who don't know, is a C++ variant. It's a constrained C++ that, with the proper formatting, will actually then compile down to Verilog or VHDL of your choice, and then you could then incorporate that into your Xilinx design that you would like. In my experience, that has easily 10 times reduction in our code and greatly accelerated our testing, and it has a lot of really cool features that I can talk more about later if anyone's interested. But the general architecture of our system is, we have our left and right camera that we need to synchronize those, so it's written into the actual memory on the FPGA. We then have the image processing, which kind of extracts the edges for the sparse data, does the stereo computing, and calculates the gradients. So that's going to read that from the DDR. It's going to write that back. And then the actual, optimization step in our SLAM algorithm to calculate the rotation and the translation is done in the photovisual odometry, which also it has a Jacobian Hessian, which is a fancy term for first and second order derivatives that does a lot of that computing. And for our design, this is a fully FPGA implemented design. And it can be, driven by the CPU, but, none of the actual computing is being done on the CPU itself. And so our initial algorithm of mapping the algorithm to the FPGA, these are kind of the high-level resources. So for a Kintex UltraScale for the space-rated variant, and these are the different, resource counts that we had, and underneath is actually the percentage of the total usage on that device. And so for the Kintex running at 200 megahertz, we used, with all the various pieces put together, we used, this is the time at the bottom, but I think each of the resources came out to be about 10% of each of the different resources in total. And we were able to run it at 30 hertz, which is in real time for most cameras, but much faster than what we would actually need to, but it kind of showcases the real-time capability of what we want. So these are some initial results. We were a bit limited on the actual real-world data that we had, and so these are kind of just two snapshots of what we had. On the right is actually a test case for our ground vehicle, so I wanted to prove that the algorithm worked before we had real-world robust data. So the orange loop is actually the ground truth, and the blue is what our algorithm was able to get. Typically, for an algorithm like this, we would incorporate the mapping portion and have what's called loop closure to kind of help tighten up that mapping. But with a localization only, this is showcasing that we're able to kind of track the location of this ground vehicle. Obviously, this isn't a satellite, but it's a good surrogate to show that all the changes that we made for this algorithm to work in space and to run efficiently still perform well on a real-world, difficult data set. And on the left, this is a bit tricky to read, but these are the degrees offset from the expected rotation for what we actually calculate. And so throughout the entire rotation of our satellite for the video that I showed you earlier, we're never deviating more than about 0.3 degrees off of what the actual location should be. And if you assume that an uncooperative satellite is, doesn't have any force applied to it, you can do a lot more advanced processing and say assume a constant rotation and all of these other factors. So what are the future goals that we'd like to do for this research? We'd like to collect real world data. We're currently working on getting a blackout room with an air bearing table to move these satellites, and on Wednesday you'll get to see a lot of that with our space robotics. Add mapping and loop closure to minimize a lot of these errors and to kind of enable more features than just tracking a satellite and localization. We'd like to add support for just using a single camera because stereo pair adds weight and power to your satellites. So we'd like to have that option. I'd like to get a full working end-to-end example. This is kind of done in pieces and done on a test environment. I'd like to get it on a more space-rated hardware and then implement more of an indirect SLAM. I kind of said we didn't use that specific version, but it actually offers a lot of complementing features that can really benefit this. So that is the end of my presentation, and I will open it up to questions.
So, okay, so what range of distance between the spacecraft and imaged object is valid for SLAM and stereo visual configuration?
That's a great question. So it really depends on how your cameras are configured. So for stereo cameras, the distance that you separate the stereo cameras apart will actually dictate what kind of range that you can operate in for those stereo pair. So there are, great equations online. I don't have them memorized, but that's kind of your first limiting factor. And then the second one is really the limitation on distance is more in what features can you actually see. So if you're so far away that the satellite you're wanting to track is just a speck in the distance, you're not really going to get enough features to actually determine, how is this thing rotating. But once you can start to see kind of the defined edges of the satellite, that kind of gives you, that's when you can start to kind of figure out the rotation. It's not really a precise answer. It really depends on what kind of camera you're using, how far away you're kind of zooming in. But you can usually change the camera lenses and the camera resolution to kind of work further away or closer up depending on what your use case is for this.
So how difficult would it be to modify algorithms for servicing cooperative satellites?
How hard would it be to adapt algorithms for cooperative satellites?
That's the question.
That is the question. I guess I don't understand what cooperative satellites mean in this context. If someone yeah, so I mean, that was the use case of this research, was to, design a satellite system, both in the robotic arm to grab another satellite and the vision system to then ideally, refuel, bring it up to a higher orbit of the such. How hard is it to adapt to these algorithms? If you want them to run in real time, and these are computationally expensive, it does take a lot of thought. I would say, I don't know if I'll be able to directly answer the question, but what I've found is a lot of algorithms have been built for, CPUs traditionally, and mapping them to more efficient processors for real-time processing, like a GPU or an FPGA. Sometimes it can be adapted easily, sometimes it cannot. It's a lot easier typically to start from the ground up with a fresh algorithm to make that work. But also real-time in space can mean, servicing it in like 10 minutes. So there's a lot of factors that kind of go into it. But I think there's a lot of newer technologies like Vitis HLS that really help speed up the adaptation of these algorithms.
Yes, kind of piggybacking off of that, if you were to seed your algorithms with a priori knowledge of what you're looking at, have you seen improvement on your performance, or does it actually slow things down to try to map to a known solution? So
we have not tested it with a priori knowledge, like, having like a CAD model of the satellite or images of the such, just because we want it to work in the most generic kind of situation. If you had an actual model, for example, you could get away with not having a stereo camera. You can get away with just a singular camera if you actually knew like what the actual size of the satellite should be, because that would eliminate the ambiguity of your system. You could also then predefine where are the kind of the key points that I'm looking for, and if you could then match the key points to that model, that could then greatly help you figure out the size and other features. So we haven't tested it, but it would definitely greatly help speed that up.
All right, so that was our last question, and I'll just say, if you'd like, you can create a channel and make sure you tag the presenter so you can continue the conversation. Thank you, Ryan. Appreciate it.